How's everyone doing? Taylor and Blake, good to see you here. Let's get Mubot awake. We got, hey, Shaq, good to see you here. What should we do? Let's put on a little chill music right here. I like the chill music. That's nice chill music. Taylor's got it. Taylor, which one should we do first and what chapter is that in? I've been running some R code here. Maybe we'll find out. I've been making some statistical models. Been making some models today for the last 10 minutes. The last 10 minutes. We'll see how it does. Good morning, Lindsay. Chapter 7 quiz. Let's go look at that here. Making those statistical models. Don't worry, it looks like there's errors. Should just run suppress warnings around it. Should have done that. Should have. We'll see what it does. We will do some Chapter 7 quiz. Closing out chats. Chapter 7 quiz coming right up. How's everyone doing today? We might do some, Oh, it finished. Oh, it finished. Okay, cool. Okay, so this is the last thing we're going to do. Meet, good to see you here. Meet, this is the super advanced modeling we do in 474, where we do what's called elastic net regression. We make tons of models. So at the end of class today, I showed the super advanced regression where we do gradient boosted models. So let's take a look over here. With the gradient boosted model, this is what I will do is real quick right here. And results of the gradient boosted models. Ooh, do we not get a better model? We might not have. RMSE, do you know, have you ever heard of RMSE, Meet? Have you ever heard of RMSE? Oh my gosh, we didn't get a better model? That is so sad. And it's the first one. Wow, we didn't get a better model. All that work for nothing. Question 5 on the practice exam. Yeah, we'll take a look at that here soon too. Thank you, Meet. So the answer is, Meet, we, according to RMSE, root mean squared error, we didn't get a better model. The gradient boosted method spent a good 10, 12 minutes on my computer running and did not find a better model than what we found with the cross-validation. Also, the RMSE standard deviation, which is our uncertainty. Oh, the bunny's doing great. Good to see you, Ford. Morty didn't eat for a moment yesterday and scared me, but he's doing great now. So the bunny's doing awesome. Ford, good to see you here. We're going to hop into a little 201 to start. I'm going to yawn. I'm going to get that second cup of coffee here soon. Second cup of coffee is going to be great. Loading up 201 as we speak. But all that output right there to tell us we didn't get anything better than just using basically vanilla linear regression. Amanda, good to see you here. And Blake, good to see you here. We couldn't open your course. My Pearson, please open my course. My Pearson just said we couldn't open your course. Please, my Pearson. And looks to be doing it now. Instructor tools and assignment manager. We're gonna grab those questions. Meet, I think you have question number 3. Taylor's got the first 2 right here. Where's Mubot? Oh no, let's look up Mubot. Mubot's over here. Waking up a student in Introduction to Statistics class. First question right there. So Stat 201, Chapter 7. Mubot is waking up. Student intro, researchers collected data. Researchers collected data. Stat 201, Chapter 7. And then next we have the manager at a bookstore wants to predict. And Stat 201, Chapter 7. A little more chill music right here. Just played that one. And sent you a Discord, the residual question about the newborn length and weight. Yep, Lindsay. Thank you, Lindsay. Stat 201, Chapter 7. Newborn baby and weight. Is that a quiz or a homework, Lindsay? Is that a quiz or a homework? BAS 320. I'm writing down everything right now as we talk about this. Good to see you. Good to... Yeah, Ford, let's throw it around. It's on the homework. That's what I thought. I thought that one was on the homework. I've got that one here last. Let's throw it on here 1,000 points. Thank you, Ford, for showing up. And we got here homework. Okay. 2 seconds. Okay, let me put a quiz on these. I think we now have everything organized. The first question right here is going to be a student in an introduction statistics class, like you. It's like, oh my gosh, that's me. I'm in an introduction to statistics class. Student in an introduction to statistics class. And first off, we see the manager at a bookstore question. Multiple managers at the bookstore. Some of them have extra parts. Let me know if I don't get the right one. Here's the first student at same Amanda, just trying to get a good stats. Nice job. Here we go over to the main screen. Let's do it. So we have the student in an introduction to statistics class. So we have here 633. A student in an introduction to statistics class at her university. She wants to model the relationship between a student's job and GPA. She collects a random sample of students and asks for their GPA and the number of hours they work a week. So both variables are what instantaneously. You see both variables are what. The number of hours somebody works and their GPA is what. The number of hours somebody works, so hours per week work, and GPA are what variables. They're both quantitative. Blake right there, 1,000 points. They're both quantitative, which is the first condition of regression. So we could talk about there being regression or correlation. Good job, Lindsay. They're both quantitative variables. She checks the conditions, make sure a linear model is appropriate. QQ straight enough, no outliers, plot doesn't thicken. She finds the R squared is 12.7. What is the correct interpretation? Don't look at their interpretations. Don't look at their interpretations. And this is good for Meath and everyone too. What does the R squared mean? QQ straight enough, no outliers, plot doesn't thicken. So what does 12.7 mean? The Y variable of interest is GPA, and the X variable is hours worked. Can you do it? You're on the right track, Blake. Yep, and don't look at their answers. I'm not even looking at their answers. I'm not looking. 12.7% of a student's GPA is accounted for by the, might be. I would say, and Taylor, good work right there, 1,000 points, Taylor. I'd probably count that. Let me see. Let me read it again. 12.7%, and I'd say of the variation in a student's GPA is explained by the variation in the hours a student work. Not whether or not a student work, but the hours a student works. So blank percent of the variation in Y. Here, I'll write it in the chat. It's blank percent of the variation in Y is explained by the variation in X. Blank percent of the variation Y is explained by the variation in X. So 12.7% of the variation in somebody's GPA is explained by the variation in the hours someone works. So let's see if one of these sounds like that. 12.7% of 12.7% of a student's GPA is, let's see right here. I think it's gonna be this one right here. 12.7% of changes. Ugh, my Pearson, you're written. Who wrote this one? 12.7% of changes in GPA can be accounted for by a linear model on hours worked. That sounds most accurate to me. 12.7% of a student's GPA is accounted for by whether or not the student works. They should literally say the work hours. So I'm a little worried about that one. This one's almost got a second place. 12.7% of the differences in work hours. She wants them all to the relationship between student jobs and GPA. She clicks around. Then she checks to make sure they're appropriate. GPA is the response. Yes, GPA is the response, the Y variable of interest. So these are just wrong right here because these have the wrong Y variable. So it should be this one. Changes are like the variation. Yeah, that's, once again, they're trying to trick you with these weird ways of writing the answers. The reason the C is wrong right here, the whether or not a student works, makes it sound categorical. It's the, and they mentioned linear model, which is very good right there to maybe say, like, I don't usually say it, but you could say 12.7% of the variation in somebody's GPA is explained by the linear model on the X variable. Like, you can get super technical. Another way of saying this, which Dr. Petrie endorses, is saying things like, if you know somebody's if you know somebody's hours worked, it gets us 12.7% of the way to understanding someone's GPA. Like, that's the amount of variation hours works explains in someone's GPA. So knowing somebody's hours worked gets us a certain percent of the way to knowing someone's GPA. Now, we wouldn't know all of it. We know 12.7% of the variation in someone's GPA by knowing the variation in their hours worked, like over the data set. So kind of a good question. That right there makes it sound categorical. It's not whether or not they work. It's the variation in the hours they work, accounted for the variation. Once again, use the interpretation I have right here and see which one follows it the most. Blank percent of the variation in Y is explained by the variation in X. So the Y variable of interest was GPA. It says the response, which is the Y, like, why are we doing this? And so the X is going to be the explanatory variable. And so I prefer to write it that way. That's the way I always do it. And then I look to see which answer most conforms to that way. There are other ways of writing it, but I just like to use a standardized format. So is that the one people were wondering about? There might be multiple versions of this. We've got researcher collects data next. Let's head back to the mic. Researcher collects data. A researcher collects data. What are those researchers doing with their data? Researcher is collecting data. The explanatory variable. A researcher collects data. Remember the timestamp? Oh yeah, oh yeah. A researcher collects data. Where is it? It's gonna be like the last one. It is. Researchers collected data. Let's go check this out right here. Researchers collected data. Here we go. So researchers are collecting data on the annual mortality rate, deaths in 100,000 for males in 20 large towns in England and Wales, and the water hardness, which is going to be measured by calcium. Hard water is water that has more calcium in it. So this is harder water right here. This is softer water. I guess I call it that. What do you notice about this relationship? Oh my gosh, all those errors. What do you notice about this relationship right here? Mostly what? Mostly what? Mostly that, I'd probably say, yeah, probably about, yeah, pretty good. Pretty good. Mostly linear. It's got homoscedasticity or plot doesn't thicken. This is a pretty good relationship right here. Not much plot thickening either, exactly. Not really any extreme outliers. The plot thickening I'm showing you with the bands right here, that the bands are about even width. So you see about the same thickness throughout. You also see pretty much a good linear model goes through. This is a very good candidate for regression. So it'd be like, yeah, pretty good right there. Little QQ straight enough, no outliers, plot doesn't thicken, looking pretty good. So yes, we like it. Yes, sir, I like it. So what would we say about this? Well, it's fairly strong, I would say. Strong is the tightness. Weak is going to be more like a circle, so it's not fairly weak, I'd say. Then it's a fairly strong, so the positive right there is wrong because it's negative, so it has to be one of these two. So linear between towns with harder waters, that means higher up here, tend to have lower mortality rates. That's going to be the right answer because harder water, you have to know that, is more calcium. So towns with harder water tends to have lower mortality rates. Here is the output. Now, you know what's so great about this? We keep showing this off right here. We keep showing this to give people some advanced knowledge, but it's not really advanced, it's what we're doing. That output you see on the screen, I'm predicting the horsepower of a car from the weight of a car. So I know how much a car weighs, and I want to predict the horsepower. So that very output you see on the screen right here, how similar does it look to this? That output you see right there on the screen, I'm going to make it real small so you can see it. How similar does that output on the screen look to what I'm showing you over here on the left side of the screen? How similar do these outputs look? Where it has coefficients, where it has standard errors, where it has t, and where it has p-values. How similar does this look to all this right here? I'm going to highlight that right there. How similar do those look? And it looks the same in jump also. So it's going to look the same in jump, whether we do it in jump, whether we do it in R, whether my Pearson presents it to us. It's going to look the same either which way. Great job, Lindsay, right there. Does that make sense? This is the output from the regression. You also see things like R squared. That's R squared. That's R squared there. You see the standard deviation. I think they're saying that that's the... Are they saying that that's the residual standard error? I don't know. They should really make that a little more descriptive. I don't think we're going to use that, though. So they're giving you all the output from the regression, which is the model and how well it does. What are these values? The most important things to know right here would be our interpretation of R squared, which is 59% of the variation in mortality can be explained by the calcium in the water. So know how to interpret your R squared. But then these values right here. What are those values in order? Like, what are those values? That is the coefficient for the intercept. That is the coefficient for the slope. So what are those values? Like in notation. What are those values in notation? The coefficient of the intercept and the coefficient of the slope. What are those values in notation? What would they be? What would they be? B0, B1, great job, Lindsay, right there. We'll throw some points in the chat. Lindsay, you are B0, B1 in that order. So then we have to know how to interpret them, which we'll probably do in a little bit. But we're just looking at the output and knowing what we see right here, because if we know what we see, we can probably answer all the questions. B0 means a town with no calcium in its water is expected to have a mortality rate of 1,799.565 deaths per million or something like that, maybe. And then we just have to look at the units of the problem. And then the slope right there means for each additional 1 unit increase in calcium water, for each additional X, B1, for each 1 unit increase in X, we expect the mortality of a town to decrease by negative 1.348. And great job right there, Blake, dropping the equation in the chat for another 1,000 points. Great work, Blake. That's what we want to see right there, is being able to write the equation, because that's the estimate of the intercept and that's the estimate of the slope. Just make sure to carry your decimals right here properly, because that's where errors usually occur. I make them too. And then make sure to do the negative. The negative is very important to the problem. You won't get points back if you miss the negative. Don't miss the negative, because it's not a positive relationship. It's a negative one. That's not a decimal error. That's a, we got to make sure we tell them it's negative, because that's dramatically changes the model from it has a negative relationship to positive. So that should be right there. Interpret the slope. So it's for each 1 unit increase in what? The slope is for each 1 unit increase in what? The slope is for each 1 unit increase in what? The slope is for each 1 unit increase, and think what X is. And you can also see X over here on the graphic. The slope is for each 1 unit increase in X, and X is what? X is what? For each 1 unit increase in X, and X is what? Calcium. Great job, Meath, right there. I know you're thinking some 320 interpretations, right? The reason Mike Pearson kind of locks us into using these interpretations, where in 320 we would say 2 towns that differ by 1 unit of calcium are expected to differ by 1.348 units of mortality, where the town that has higher calcium is expected to have lower mortality, because it's towns we're looking at. So 2 towns that differ by 1 unit of this right here. For each initial increase in X, we require to decrease. And this is, and then the on average is great too. Great job, Blake, right there. Really good knowledge for test 2. For each 1 unit increase in calcium in parts per million, the model predicts a decrease, negative slope. So the answer right here, just the decrease. Very important to know that right there. Explain the meaning of the y-intercept. The meaning of the y-intercept is when X is equal to 0. So when calcium is equal to 0. And so explain the meaning. The model predicts that a town with 0 parts per million calcium would have the intercept value. So, and that's probably, I don't know if you can have no calcium in the water. Maybe you can. So it's going to be when X is equal to 0, which X is calcium, then the model predicts this value right here. That's a very good way of saying it. Like, this is excellent, because it's got predict, all that good stuff. The largest residual has a value of 83.3. What does this mean? So if you go back and look and we draw the model, the largest residual is 83.3. And let's do a hypothetical. What does that mean? And so Blake, does it make sense when I draw this out right here? Like, if you say, like, just hypothetically, we're saying that's the largest. I know this one down here might look like the largest right in there, but don't worry about the other one that might look. But if that's the largest residual, the town's what calcium was what? So the residual is 83.3. So the town's actual mortality rate, so maybe it's up here at 170, 80, and this would be like 169.7 right there. It is the actual was higher than we predicted it to be. It was 83.3. The town's actual mortality rate, because that's what we're looking at on the Y scale right here. The town's actual mortality rate was 83.3 higher. And that's just a hypothetical. Like, it's good to draw things out and to be like, well, that means it's going to be higher than we predicted it to be. So the town had this many more deaths, and it is in units of 100,000. So make sure, I think I've missed this one before. You have to do the units of 100,000 because it's per 100,000, because it's a unit thing right there. I've missed that before. I know that. The hardness of a certain town was 146. We're probably going to make some predictions right here. Use the values in the regression model to predict the mortality of this town. So all we're going to do right here is do what, since we know right here, and it is in des per 100,000, so we don't need to do any unit changes. All we're going to do right there with 146 is what now? What do we do with 146 to make predictions? What do we do with 146 to make predictions now? So it says predict the value, which means a y hat. Great, Blake, you're just on fire today, Blake. Great work. I feel like you really understand regression well. And Meath, does this help out other people who've taken 320 or maybe are taking 320? Does this help out right here to do these and understand how this works? Because we can do all this with code. Plug it in right there. You got it. And Lindsay, thank you so much. Really trying. Blake, yeah, you're doing great. Thank you so much. Like, I appreciate it. And then what you want to do is, if 146 is right in here, you want to think, does that make sense? Yeah, it looks about right. I think we've done it. Just plug the number in. Hopefully we don't miss anything. 3 decimals. There we go. This is a huge help. Yeah, keep doing it. Explain the meaning of the R squared. So it's 59% of the variation in mortality. I think this one right here, 59% of the variability in mortality can be accounted for by a linear model on calcium concentrate. Exactly. So it's blank percent of the variation Y explained by the variation X. Please tell me I didn't miss anything. Woo! All these long questions right here. Really good question once again. Few tricky parts. Make sure to get the units right. Make sure to get the decimals. Don't forget your negatives. But good question right here on the concepts. And do remember R squared is blank percent of the variation Y is explained by the variation X. Just have your answer ready. The manager of a bookstore. Yeah. The manager. Oh, we got that one next. You got it. Here we go to the main screen. Whee! Whee! Need help with the interpretation question on the 7 question? Yeah. Let's go find the manager at a bookstore. Let's go talk to them. The manager of a bookstore. Boom. Let's go do this right here. We already got it ready to go. No music even. Manager at a bookstore. 2313. Manager at a bookstore. Here we go. Okay. The manager at a bookstore, and then we have the birth weight coming up. Yeah, we do data analytics. Let me put that on here. Got that after Meet's question, I think. There we go. It's on the list. Data analytics 5. Thank you, Tara, so much. Stat 201, data analytics number 5 on the list. Good to go. We still got a lot of time. So here we are. The manager at a bookstore wants to make predictions for the number of sales based on number of people working. And we have data right here. So with this data, watch this process. You ready? You need to click right here. Then you need to click right here. Then you need to copy to clipboard. Slow the video down or pause it. Make sure you follow these steps exactly. Now you need to hit Control or Command C. Control or Command C. Now that you've done this, you're going to go to jump. We got a jump going here. Good, we're good to go. Okay, you're going to go into jump. And inside of jump, you're going to go to File, New, Data Table. File, New, Data Table. When you go to File, New Data Table, don't click inside of it. Don't click inside of it. Don't click inside of it. Go to Edit, Paste with column names. And what color for 1,000 points should you see over here if you've done it properly? If you've done this properly and the column names appear at the top, what color should you see? And do File, New Data Table again, paste with column names, but don't click inside of it. Blue, you got it, Tara, right there. If you've done it improperly, you'll see red. No, it's categorical. It's not categorical, it's quantitative. Great job, Tara, right there. So make sure the data is blue, meaning quantitative. If you've done it improperly, open up a new data table and paste with column names. Make sure the data pastes in here properly. Copy exactly. Blake dropping those instructions. You got it right there. Be a Jump Pro. It's a joke. It's a pun on Jump Pro. The data, Jump Pro. Find the estimate of the slope. So now that we have the data inside of Jump, make sure you followed the steps right there very carefully to get the data inside of Jump, which makes our lives way easier. Now you're going to go to Analyze Fit Y by X. Blake's got it right there in the chat. Blake, thank you so much. We're dropping Blake another 5,000 points. Blake, you really, it's when some people, I know Jump's kind of complicated, but like using it can make life really easy, because now we can just say, I want to analyze my Y by my X, like 2 variables, bivariate. That's the univariate. That's the bivariate. And so we want to say, let's take a look right here at predicting our sales, which is the why do we have certain sales. Yeah, it does make life easier. I think a lot of people are like, I don't want to use this program, another program for another class, but it's like, yeah, you just put the Y variable of interest, you put your X that explains it, and you click OK. So we just choose our y variable we want to understand and the x we want to explain it. Yeah, that one. That's my Pearson being mean. And so here you see you have a mostly linear relationship. Does that mean more people working cause you to make more money? No. It doesn't mean more people working is associated, but it might be a scheduling thing, like you schedule more people on busier days. So now we're going to go to the red arrow right here and go to fit line. So the red arrow right there, fit line. That's where we fit our line. Boop. And there you go. The equation of the line is found right here. This is the intercept, and this is the slope. That's the x variable name. That's the y variable name. And take a look. Remember just a moment ago when I said everything you're doing inside of jump is done in the other classes? I was showing R just a moment ago over here, and that output right there on the screen that I've highlighted on the left is the same output inside of jump right here. If you're watching one of the previous questions where you have the estimate of the intercept, which is B0, the estimate of the slope, which is the x variable, which is B1, your standard error, which is your uncertainty, your t ratio, which is the ratio of the two numbers, and your p-value, which is the statistical significance, which is noted by the statistical significance of the slope, which is also seen under here on the analysis of variance. Look right there, 5.877 to the e to the negative 6. And right here, the same p-value. Show me it. You got to hover over it. We're going to spend all day. Oh, there we go. 5.877. So this p-value right here is the p-value of the model, the p-value of the slope, which is used in the ANOVA. We don't cover those topics as in depth in 201, but there's lots of cool things. Like if you square the t, you actually get the f right here, the f right there. The t squared is the f. Where's my f statistic? 23. So if you square this, it's almost exactly 23. That's the square root of 23. Really? There you go. Square root of 23. You don't need to know that kind of stuff, though. That's just fun math stuff. We don't do fun math stuff. We do interpretation. We do data analytics here. So we need to know the B0 and B1. The regression equation right here is the B0 and B1. Just make sure you know that when you have output like this, you have B0, which is the intercept. You can see it down there at 8, and the slope is about 1. And we see that down here, the B0 and the B1. Make sure to know that. So over here, it says, what is B1? It's just asking me the slope, the estimate of the slope. The estimate of the slope is this value right here. Also know that that value, the estimate of the slope, is seen right here under estimate of x variable, which is slope. There you go. Round to 3 decimals. There we go. What does B1 mean? Now be careful. I really like adding in the expecteds. So B1 means for each additional, or on average, for each additional person we have working, we would expect sales to increase by 0.935 on average. And I think I have some units right here. It means that on average, no. It means that on average, no. It means on average, an additional increase of this in sales is associated with each additional person working. That sounds about right. And they don't give you the value right there because they don't want you to know, and it's in thousands of units. It means that on average, an additional increase of this in sales is associated with each additional person. So for each additional X, we expect sales to increase by this. Be very careful, it's not cause and effect. Let me read this last one. It means that on average, an additional increase of this in sales people working, no. With each dollar, this reverses the X and the Y relationship. So this is no. For each additional increase in salespeople, no. The X variable was, no, that's saying the Y because it's saying the, it's so weird how they do that. But it means on average, an additional increase in sales is associated with each additional X, which is each additional person working. Find the intercept right here. The intercept is the value of B0. So B0 is going to be this right here, also seen in the output down here where B0 is at. B0, B1, just think about intercept is when X is equal to 0. B1 is for each additional 1 unit increase in X, hence why it's associated with the X. There's the value of B0 and 3 decimals. So that's going to round right there nice and neat, I believe. Don't tell me I'm wrong. What does the B0 mean? It means when how many people are working. What does B0 mean? On the B part, what about the B part right here? Which explain go explain more detail, Blake. What do you mean by like how you get this right here? How do you know this? It's a weird way to word it, but we would say for each additional person working, we expect the sales to increase by, did you go off the interpretation definition? Yeah, so it's for each 1 unit increase in salespeople working, which is X, for each 1 unit, because I'm rewording theirs, for each 1 unit increase in salespeople working, we would expect the sales at the store to increase by B1 on average because the sales is the Y. So our interpretation is for each 1 unit increase in X, we expect Y to increase by B1. Does that make sense? That's ours. I'll type it out right here. For each 1 unit increase in X, we expect Y to increase by B1 on average. So they reversed it though. They just reordered it. It's still correct, but they said, I'll show you the correct, like the way we did it. For each additional salesperson, we expect sales to increase by this much on average. That it's a total rewording of it. So this would be the right, like I'm 99% certain, because this is for each additional salesperson, we expect the sales to increase by this much on average. So if you look at, they've just kind of put the last part first, talking about the increase of Y associated with an increase in X. So just make sure the each additional right here is the X. And then the Y right here is the prediction of the Y, or the expected prediction. Does that make sense? And then what does the intercept mean? Visually, what does the intercept mean? What does the intercept mean down here? What does that intercept mean? Which is kind of weird, which we don't have data at. Makes sense. What does the intercept mean? The intercept means what? When we have what? So what does the intercept mean? The intercept mean when we have what? Don't look at their answers. The value of Y when X is equal to me. So, and what does it mean? When the line crosses, and so, but then how would we interpret that? How would we write that? Like, pretend this is the test now. How would you interpret that on the test, which is 12 points of the test? Also, meet good stuff here for 320. How would you interpret that? When salespeople working, when we have what? Well, that's the, well, you've kind of combined the slope and the intercept right there, Lindsay. So remember the intercept, here's the slope interpretation. We just did slope a moment ago. That's slope. Intercept is when X is equal to 0, we expect Y to equal B0. So then try writing that out. I've put the blank interpretation in the chat, but try doing the intercept. And then think about what that means. When, what is X? You have to say what X is. This good review right here, because this is what the test is like. When there are no salespeople working, we expect the sales to be, and then I think it's $8,000 exactly. The Y-intercept, because it's where it hits the Y-intercept right here. That's the Y-intercept is when X is equal to 0. So Meath has it right there. I think it's at $8,000 because I think the sales is in thousands of dollars. So when there are no people working, in our store, we expect to make 8,000. No worries. Meath, thank you. 1,000 points right there. And then Lindsay also has it. And then technically, I'd probably count that. I'll have the graders grading it. Maybe it'd be a half point out of 4 off. But when the number of salespeople working is equal to 0, we expect the sales to equal $8,000 on average. Or if we times this down here by 1,000, we could get the, like in units of thousands. We expect the sales to be that. And that sounds really weird, right? Because when no one is working, how can we make sales? Does that make sense? Like this is probably, it looks like an extrapolation of the model because it's outside the X bounds of the model. And so it doesn't really make sense right there. Like maybe it'll go that direction with this. It means that on average, the expected sales is, no, we're not gonna, no. Yo, it's doing that, right? Yeah. The expected sales is this with 0 salespeople working. It doesn't make sense because it's unlikely that any sales will be made if 0 salespeople are working. That sounds right. It means that on average, the sales will equal, they put expected. Yeah. So this one says will. We don't like will. Sorry, we like wills, but we don't like saying will in our interpretations. I think that's where they're going that. It's the expected, not what it will be. It makes sense. No, they're really going wrong on that one. It means that on average, the minimum, no. It's the expected. Write down the equation that predicts the number of sales from salespeople working. Wait, what? I thought we just did that. Do we not write the equation? Oh, we're just, yeah, okay. We did. All we do is we take B0 right here. And we drop in that. There's B0, and we take B1, and we make sure to round them. And it wants it rounded to 3 decimals. This one did round. Remember, we literally are just taking the values right here from B0 and B1 respectively, which are seen right here, B0, B1. It's a really great question. So, till I get one thing wrong, and then I get mad. And say, horrible question, because I rounded wrong. For 18 people working, what is the prediction? What do you do? How do you make predictions with your model? And it wants it actually in dollars, it looks like. So we actually are going to convert this by times it by 1,000. Hey, what's up, Blake? What do we? It says for 18 people working, what would you do? Which I think might be an extrapolation of the model. No, it's not. It's within the bounds of the X. For 18 people working, we should get somewhere about there, around 24 or so. Plug it in. Then we'll have times it by 1,000. So you can look at your model to make sure you're doing it accurately. We're just going to plug 18 into X right there. 18 times 935 plus, I said about 24. There it is right there, right at 25. Just plug it in. Now, also, you need to times this by 1,000. And there it is right there. 24,930. It says round to the nearest $10 as needed. So once again, all we did was plug in 18 right here. Do realize it's also telling you to do it in thousands of dollars. So we just found the what. That value we see on the screen is the what value. According to the regression model, that is why it's got a hat on it. That is the what value. That is the what value. That is the predicted. So when we look at this model, we predicted on the line. Here's where we predicted. But the actual is right there. So what are we going to find right here? So we found, I'll zoom in on a little bit. Can I get it all on the screen? Nice. There we go. So we have the predicted amount, which is Y hat. We have the actual, which is Y. So what do we find right here? The hat means predicted. Great job. So what would be this? What would be the answer to this question? The residual is their difference, but think the actual is higher than the predicted. So the actual is up here, and the residual is their distance they are away. So it's a positive difference. So what's the answer? We can solve it out mathematically down below, but can you tell by looking at it? So it's how much higher, because we know that the actual is higher. The actual is what it actually is, which is the point itself. That's the actual. The prediction right here is the line itself, and the residual is their difference they are away from each other. So what would this answer be? So remember, it's actual minus predicted. I'll start writing it out. Yep, great job, Blake, right there. Yep, it's just the difference they are away. So it's actual minus predicted. And so that right there is the difference. Blake solved it in the chat, is equal to 1070 right there. And that's the distance those two values are away, which is their residual, meaning that the actual was 1070 higher. And then look when you see it and say, is the actual 1070 higher? It is. So the answer right there should be 1070. Now be careful. This is where sometimes we get a little bit tricked. When we have right here, has the original estimate for F been over or underestimated? So if you look at this visually, oh my gosh, go in Photoshop again. If you look at this visually, 2 seconds right here, everybody. If you look at it visually, did we over or underestimate it? Be careful. Did we over or underestimate it? So the model is the estimate. Did we over or underestimate it? The model is the estimate. Did we over or underestimate it? We underestimated it. Remember, the model is the estimate. So that's the actual. The model is underneath it. So we underestimated it. So it's weird that a positive residual means the model underestimated it. Does that make sense? Like this, the residual here being positive because we're above the line means the model is underneath it. Seeing it visually, I think, can help to be like, oh, here's where we are. We underestimated it, and there's a positive residual because the point of what actually is the value is higher than the model, so we underestimated it. I think that should do it. I think we got it right. Oh my gosh, wrong buttons. Check all the answers. Check answers. Woo! Got that 100. We're on a roll today. Got a little, oh my gosh, right here. Just got a little hacker man. W right there. I think we're about to do that birth weight question on the homework. And then we got some 320. Got some more stuff coming up right here. Moobot's in the chat. Birth weight question on homework coming up. Hacker man ending. Hacker man over. Great job, everybody. Let's head over to the main screen and get some birth weight question. Good work, everyone. Good practice. That's what we're here to do, is get that practice, practice, practice. Homework time. Little energy, energy, energy music, as BTS once said. Get that energy, energy, energy. Blackpink's gonna be in our neighborhood, and I won't get to see them. Tickets are like cheap tickets are like $400 or $500. Nice tickets are like 2,000. Craziness. Darn scalping at tickets. The birth weights. Can't go see Blackpink. Which one? The birth weight is chapter 7, right? Chapter 7 birth weight question. How does the birth weight question start? What number is it? Homework stays the same. Oh, I found it. It's number 3, right? Yeah. Awesome. Hey, what's up, Emma? We're about to do another 201 question. We're going to do some visualization at 320 coming up. And then data analytics. We got birth weight question. Data analytics. We got time for a little bit more after that, too, if you'd like. So, 4 to 2. Here we go. Let's do it. Okay. This one is asking about a residual. So what do we get right here? Let's break this question down. Little tiny question. A lot of work. Tell me by the colors what I'm highlighting right here. Are you ready? What is that color? What is this one? What is this right here? And then what is this? The predicted weight. So that's the Y variable of interest. We are predicting weight. So that means we are predicting that. Correct. No, that's Lindsay. We're going to get this. Then this is the intercept. That is the value of a baby of length 0 is expected to be negative 6.17 kilograms. So that's a illogical or meaningless intercept. The slope is pink for, that means for each 1 unit increase in length of a baby, we expect its weight in kilograms to increase by 0.1819. And the X variable of interest is the length. So there's the equation right there written out for you. And you can see the components you should know, like we are predicting Y, hence it has the hat. The intercept is when X is equal to 0. And the slope is for each 1 unit increase in X. So know how to interpret all of these. Like know how to say, if a baby had a length of 0, we would expect its weight in kilograms to be 6.17. This is illogical because babies can't have negative kilogram weights, nor can they have a length of 0. We know how to interpret the slope. For each 1 unit increase in length of a baby in centimeters, we expect its weight in kilograms to increase by 0.1819 on average. So there we go. Know those interpretations. So the right here, circled in blue, the centimeters is a what value? Centimeters is a value of what? Centimeters is a value of what? Centimeters, because is a value of what? One letter you need in the chat. This is this baby's what value? One letter. This newborn baby has a value of this. It's their length, right? So that means it's the what? It's the X. Exactly. That's an X value. Then this over here is what they actually weigh. That's what the newborn baby actually weighs. This newborn baby is 48 centimeters. That's its value of X. And then this newborn baby actually weighs 3 kilograms. Does that make sense? So what is that value right there? 3 kilograms is its what? That's what it actually weighs. This baby right here weighs 3 kilograms. So that's its what? Like it actually weighs that. That's, you weigh it and say, yeah, it weighs 3 kilograms. That's its what? It's its actual. And what do we write for notation for that? That's its Y. And that's what Y means is actual. That's not its prediction. We're not saying, I think it'll weigh. Yeah, exactly right there. That's its actual value. So residual we'll find here in a moment. But now we've marked all the notation. We know every single thing we have. What is the only thing we are missing right now? Like we know X, we know slope. What is the only thing we are missing right now? What is the only thing we are missing right now? Like I know, I'll underline what I know. I know the Y, I know the X, I know the X right there. That's the X we're going to use. I know the B1, it's right down there. Those are the values. I know all those values. What do I not know? What do I not know right now? To find a residual, the formula for a residual is actual minus predicted. So residual, which is E. So and close, Lindsay, we wouldn't say the actual number for what. I mean, that's kind of like we don't know what the prediction is. So I wouldn't throw actual on it because it's just the prediction. Like, what do I predict this baby to weigh? Does that make sense? Like, if I know how long this baby is, what do I predict it to weigh? So what we're going to do right here is do what? So how are we going to get this prediction? So look at what we have on the screen and think, how am I going to get the prediction? Because we're really close to getting our residual. We have a lot of the components. We know the baby is 3 kilograms. So now we want to find out that E. We plug in exactly. What number do we plug in, though? You're right. I know. Like, so what number do we plug in? Because we've written all in the notation right here. This is it's a very small problem, but it's really great for notation to know like exactly how you use things. Plug 48 in for the X. You see how we've identified that for X? So now we can calculate the prediction for the baby. And great job, Emma, right there. We're going to plug 48 in right over here for the X variable right there to make a prediction for this baby. And then take 3 minus that, so 3 minus that, right? Because the actual minus the predicted. So all we're going to do right here is take, and I'm just solving with 3 plugged in. So we're just 48, excuse me, 48, 48, 48. Emma right there, 1,000 points. Emma, 2,000 points. You did a little correction on Brian, which we love right here. Emma's got the formula in the chat, just plugging in 48 right there. Take 48, plug it in, 1819, take and subtract from that minus 617. There we go. And that's the prediction. So now that we know the prediction right here, 2.5612. What's the residual about? We could estimate it. So we're just, is the residual positive or negative? And so think what that means too. So the residual should be 0.4388, I think. Is that right? It's positive. So that means this baby, the prediction, we'll do it in blue right here. That means this baby, what? Yay! Nice job. Awesome. Lindsay, great work. It's something. Lindsay, 2,000 points awesome for hanging in here. Really good notation review. Such a tiny problem right there. So that means this baby weighs more than it was predicted to weigh. So I've got it highlighted here with the same colors. The line being the prediction right here. Like this is all the prediction values. Then the residual being positive right here. The baby weighing more. So the baby would have to have a value that is above. So if you were to mark these axes right here, the baby was predicted to weigh 3. The baby actually weighed 3. That's its actual value, but it was predicted to weigh around 2.5, a little bit more than 2.5. Thus, the residual is the difference between the two. The baby weighs more than it was predicted to be. Yeah, this is what we do right here. A little small question, but it's all about that notation. So actual minus predicted, that is the residual. We got it right by doing the math in our head. I always like doing math in my head to see if I can get a good guess. 3 decimal places, round up. If you entered that extra decimal, just let me know. Oh, and then we got right here. What does this say about him? The newborn baby weighs this many more than predicted. Exactly. So we actually figured out the next part of it because remember, a positive residual means you're higher than your prediction. That should be right there. That's a really great question. And try doing the drawings, try doing the visualizations to do. You might say, well, how do you know the line looks like that? I don't. I just kind of drew like a line that goes up and then right here. I mean, I guess I could have put the intercept. Well, some line would, I don't know. It's just a quick sketch that the residual should be positive. And that's really a great question. Really good review right there. Check it out. We're going to do some 320 really quick right here with the practice exam. But stay here if you want because it's going to be very similar because 320 is doing regression. So I bet it's a regression question. So let's check that out. Excellent work, everybody. Really good practice. It's all about that notation.
Notation, brother.
Thank you, Leo. It's not Leo, it's me, but Leo came up with that. You'd be here every class saying notation, brother. Notation, brother. I don't think people realize, like, even with you being a name in the chat, like Lindsay and Blake and Amanda and Emma and Meath, Like there's people I don't forget for years to come who are just a name in the chat. It's really great that I got to meet a bunch of people though. So I got to meet people when I went to campus. I'll be back here coming up soon. But it means a lot to me to like have people here, have people chatting. It's what we do. So we learn together. We practice, we learn together, and I really appreciate people just being here. Yeah, I'll be here. Yeah, we're just that awesome. Yeah. So just be here, practice, learn together, ask those questions. Whenever you got a question, just let us know. That's what we do. We learn together. 51, 4-3. Let's go check it out. I might do a few of these. Q5 Part J on the practice exam. Oh, you're not talking about this one. You're talking about the practice exam. Oh, wait, 2 seconds. Q5 Part J. Is anyone close to the Jolly level? Ooh. I think it's you, Blake. Isn't that the... Where's that one at again? You might be the only one close to it, Blake. The Jolly and Morty fan club. Where did we put that at again? Let's see if people get that. Oh, wait. Emma's got it. Did you not see Emma's level right there? Yeah, under the modules. I realized that, right? Look at Emma's level again. We just added that. Yeah. Look at Emma's points right there. The Jolly and Morty fan club. Morty's doing better today. He was like not eating yesterday. And I was like, well, just for a moment. He's probably full. I don't want any more lettuce. Got a little scared. Not eating the lettuce. Practice exam 1 or 2? Practice exam 3. Okay, let's go practice exam 3. Oh my gosh. Love it. Outlier. Your theory is wrong. He's just gonna go erase it. Okay. This is number Q5 Part J. Q5 Part J. This might be Q5 right here. Q5. Okay. What do we got right here? What are these graphics? We might just do a lot of 5 right here and talk through this. What are these graphics? What are these graphics? And this might go a little more in depth, Meath. Might cover 1 or 2 things we didn't mention. So, thank you so much, Emma. What are these graphics? All classes should know what these graphics are. These are scatter plots. They're scatter plots. The stronger relationship, we're predicting somebody's percent body fat. So the stronger relationship is, just think about it theoretically. There's a stronger relationship with predicting how much body fat you have on you if you look at someone's abdomen, their abdomen measurement versus their wrist measurement. Like there is a relationship with wrist, but abdomen has a stronger relationship. Just visually speaking, there are some outliers. Like this person has a larger abdomen, like they're far away from the model right here. Does that make sense? If a model were to go through this data, it would probably go through there. And this person looks to have a very low residual. Their actual body fat is a lot lower than we would have expected with they actually have the largest abdomen. So pretty interesting right there. We have the coefficient of the slope for the abdomen model. We also have the intercept. And this would be, the coefficient of the slope would be 2 people who differ in their abdomen measurement by 1 unit of abdomen measurement. Is it in centimeters? It is in centimeters. 2 people who differ in their abdomen measurement by 1 centimeter are expected to differ in their body fat by 0.58% body fat, with the person who has a larger abdomen measurement expected to have more body fat. We could do the same for wrists. So we have right there, we have the ANOVA. We could calculate the R squared right here. We talk a lot about this output because we should know what it is. If you add these 2 values, you get the total variation that exists. That is correct. So the total variation that existed from the what model, so 324.74, this is the total variation that exists from the what model right there. Yeah, you got it, Wes. That is the total variation that exists from the what model. We talked about this in 474 today. That is the total variation that exists from the what model. Throw West 1,000 points in there. This was brought up in 474 today. A lot of these topics converge. This is why I love our classes, because we're talking regression, which we do in 201. We're talking 320 stuff right now, which we then do in 474. The total variation that exists from the mean of y is known as the what model. The total variation that exists, it's on the screen right here if you take a look. This is elastic net regression, 474 concept. Talking about that here in a little bit in class. So the total variation that exists is calculated from the what model. The total variation that exists is calculated from the what model? The naive model. The naive model is the jumping off point. Got the hiccups. The naive model is the jumping off point. what does our model try to do with the error? Our model tries to think of something R, tries to what the error that exists. The line is trying to what the error. The line is trying to what the error. The line is trying to what the error. It's trying to make smaller. It's trying to reduce the error. It's trying to reduce. To reduce, exactly, Meath, yeah. So the reduction is this value right here. That is the reduction from the x. This is the unexplained. The reason this is 1 is because this brings one coefficient to the model. That's why the 1 exists. And then this is on average for the one coefficient what we get. These are the means right here, over here. It got a little bunched up, but these are the means. And this is on average per residual, the error per residual on average. So let's look at the reduction right here. The reduction we have is 9,984.1 out of the total. And what did I just calculate? I just calculated what value by looking at the amount of reduction we have. So I just looked at the amount of reduction out of the total, and I literally just calculated what? So nice, Blake. I just calculated what by saying this is the amount of reduction our x brings. We just calculated r squared. So r squared is literally the reduction, or like the percent of variation we explained, because it's the reduction in the error that there was from beforehand to now. So a lot of these concepts converge right here. The equation of the regression model is going to be what? Well, we have to do the b0 plus b1x. So it's b0 plus b1x. And make sure your y variable of interest is body fat. So the body fat right here, this is selected. So body fat right here is your y variable of interest. And then you have the b0 right there. And you have the x right there. Good stuff. So once again, does this look, 201, does this look like writing the regression model? Does this look like exactly what you're doing right now in 201, where you have to do B0, there's B0, plus B1, there's B1, and X? Does this look just like you're doing right now? So people can tell you, knowing 201, if you take 320, you're going to do a lot of the same things, and your knowledge is going to help because 320 is all about regression. So just write the regression equation, y hat equals B0 plus B1X, and we were literally doing that 2 seconds ago right here, writing the same equation, identifying the B0 and B1, and it's the same sort of output whether you're doing it in jump or anything. You will see the same sort of output down here, B0, B1. And then if you know the output, you can identify the estimate of the intercept, estimate slope, and there you go. Your advisor worries that the regression model is invalid because the intercept is a negative number and impossible body fat percentages. Explain to him why this doesn't invalidate the model. So this is a written answer right here. The intercept would be when people have an abdomen measurement of 0. That's a huge extrapolation of the model. When I say we're extrapolating on the model, what am I telling you? When I say that would be an extrapolation, what am I telling you? To say you're extrapolating, which is a chapter 8 concept, to say you're extrapolating is what? You're doing what? You're not just extreme value, you're going outside the x bounds right here. So an extrapolation is when you go outside the x bounds of the model. So an extrapolation is outside the x bounds of the model because the model is created within this region right here. So if you're extrapolating, you're going into areas where your model doesn't have data. So I'd say the intercept isn't a value that we have data around, so we're not going to use the model for those purposes. That would be an extrapolation. Yeah, it just tells us when x equals 0. There are no people with an abdomen 0, so this is meaningless. We wouldn't care. It's meaningless. Exact. I know this is just like 474, right? And it's just like 201. All these concepts right here are very much used throughout all the classes. To interpret the slope, what does this mean? And we did this earlier. Two people who differ in their abdomen measurement by 1 centimeter are expected to differ in their body fat by 0.6, where the person with a larger abdomen measurement is expected to have a larger body fat percentage. An individual's abdomen size has increased from 100 to 110 over the summer. What does that mean? So how does our interpretation work? The start of the interpretation is 2 individuals. If somebody increases, the model doesn't talk about people changing. Do you remember the example yesterday? I think we did it during Kahoot, where I said, I want to predict my height, but if I gain more weight, what does that mean? Well, it doesn't mean I will change. Yeah, thank you, Amanda, right there. So the model is not about cause and effect. Like, what does this mean if somebody gains and has a bigger abdomen size? It doesn't mean they will change. Especially if someone gains weight, it doesn't mean they will get taller. It's about 2 people who differ. So that's the important thing to know right there. The standard error of the slope, which is the uncertainty in the slope, while the root mean square error is 4.15, the root mean square error is the RMSE, which is up here in the output, the residual standard error. So that is the typical miss, which is also our bias in 474. There's the bias of the model, how bad the model does. So 474 right there. So the root mean square error, the typical miss the model makes, very important for our 320 class, is this: your advisor is confused what these two mean and how they're different. Explain to him what these quantities mean. So the standard error of the slope is your uncertainty in the slope. We use the standard error of the slope to create what's. This is very important for the test too. I would use the standard error of the slope to make what's for the slope. What do we use the standard error? Because it's our uncertainty. It's like, I think the slope's about 0.6, but I could be off by about 0.03. I'm rounding the numbers. So I think the slope is about... So I think the slope, and you'll see some 201 right here. You ready? I think the slope is about 0.6, but I could be off by about 0.03. I could be off by about 0.03. So what do we use the standard error to do for the slope? We use it to make what's. I could be off by this amount. Oh my gosh. The standard error of the slope is your uncertainty in your estimate. That was the estimate. We use it to make confidence intervals, yes. So the standard error of the slope is how much you could be off by when you're estimating the slope. So that's our uncertainty in the estimate of the slope. And if you go out 2 standard errors, what percent of the curve have you covered? If you go out 2 standard errors, what percent of the curve have you covered? 2 standard errors, you've made a what? 201 will know 95% confidence interval. There you go. So what is the margin of error of this interval? What is the margin of error of this interval? Last question on this one. What is the margin of error of this interval? What is the margin of error? Be very careful. Remember what margin of error is. What is the margin of error of that interval? I'm showing you visually what the margin of error is. Exactly, and you can do it that way, and so it's 0.06 exactly, divided by 2. So you can see right here it's 0.06. So the margin of error right there of the 95% confidence interval is plus or minus 0.06. And you could rewrite your equation or the interval as 0.60 plus or minus 0.06. So that's got it right there. Just understanding conceptually and visually what's going on. Good stuff. And really good question, Meat. That's why I'm spending a little bit of time on this. So there goes that. And I think you said F is the one, right? The reduction in sums of squared error. Wait, did you say F? When using the model is this the one right here you wanted? Is it F? Or is it H or something? It's a long one. J. Okay, so yeah, the reduction, we talked about that, is in the output right here. This is how much our X does for us, so it's just right there. The reduction in sums of squared error is one way to determine the significance of the model. This reduction that the regression accomplishes is with respect to comparing the sums of squared error by predicting the average. And what is the average right here? The average is known as the what? The average of all the y's is known as what? The average of the y values is known as the what model. Once again, review from 474. The average of the y models, which is the most basic model possible. The average of the y model is what? It's on the screen. Don't worry about elastic net regression. When do we do our final projects? Oh, it's a good question. I think like a week or 2 before the final, I think, Wes. I think the time might be posted. Good question, Wes. The naive model, the mean. So it is the mean, and it's known as the naive. So it's the average, it's the naive model. Based on the regression output, is the regression model statistically significant? So this, you said it's J, right? We're going to J. So is it statistically significant? Yes, and that is 201. You should know. So the statistical significance model is the significance of the what variable. The statistical significance of a model is the significance of the what variable. The statistical significance of a regression model is the significance of the what variable. The intercept... It doesn't matter! The intercept doesn't matter. The statistical significance of it is the significance of the x variable. So that is what makes the model statistically significant right there. To determine if the model has any practical significance, we look at R squared, code its value, and explain briefly what it tells us. 66.21% of the variation in someone's body fat measurement is explained by the variation in their abdomen. So when you think about if this is important, we don't check the p-value given at the bottom. That it's the same one. They are. That is correct. In the simple world, the p-value of the ANOVA is the p-value of the whatchamacallit, the p-value of the x variable. And they actually share a nice relationship where if you take the t right here, the t value right there, this is just some math fun. If you square that t value, 22.13 times that, you actually get the f statistic right there. So they're literally one and the same. Like mathematically, they can be derived from each other. So the t right here, this t, which calculates this p-value, can derive that f down there, the 489. You don't have to know that, but this just shows like they literally are connected and they will arrive to the same p-value because the f is sort of a similar way of calculating it. It's just another test. When we do the multiple regression, yeah, they're both the same. The ANOVA p-value is the significance of the model. The x is the significance of the x, but the x is the model. Now, in the multiple world, we'll have multiple x's, so the singular x is no longer the significance of the model. The ANOVA will be. Does that make sense? The ANOVA is always the significance of the model. The x is the significance of the model here because the x is the only x variable. If we have multiple x's, then the individual x's will be the significance of each individual x. Then the ANOVA will be the significance of the model. Yeah, that's Meath. You're learning the advanced topics right now too. If you know that the ANOVA is always the significance of the model. If there's just one x, then that's it. 95% confidence interval for an interval with Oh, so this right here, I've never done these by hands. Wait, what is one? All right, we're not gonna calculate these by hand. Woo. So the reason this is significant is because like if you know someone's abdomen measurement and you know about tons of the variation in their fat, that sounds pretty good to me. Sounds like you understand about 2/3 of the variation, as it says. These are the confidence intervals right here. Circle the interval that is appropriate for predicting the average body fat among all men with a 33-inch waist. So if you're doing this for all men, you would want the prediction interval. Because we predict for one individual, we have confidence in the mean. So predict for one. That's why we use the predict function. Predict for one. And we have confidence in the mean. Oh, so wait. Because it wants for all men. So that's going to be the mean. There we go right there. So you predict for one and you have confidence in the mean. Good question right there. I don't think I put much on the test on that. Really good question. And there's a bunch right here. Whew. That's a long question. So how can we find these values on the exam? I wouldn't have you find these by hand. What you would do right here is you would go to predict and you do your model and you do type equals confidence. And nope, I'm going to do interval. There you go. And there is confidence intervals or prediction intervals. And we might talk about these a little bit today. But there's prediction intervals right there, which are for one individual. The other one is for all individuals right here, the confidence interval for the mean. This is also shown to you visually in the visualized model. I'll mention these a little bit today. I don't think I put much on the test on these, though, so that's good news. Right here is your confidence interval. Confidence interval is for the mean of the line, which is the tighter one, and prediction intervals are for all x's right there. I think we have just enough time to do a little 201. Does that make more sense right there, Meath? How is that doing with the knowledge? Prediction intervals are for one individual. That's the keynote. Confidence intervals are for the mean of the line, which is all individuals. You predict for one person and you have confidence in the mean of the line. Good way to remember right there. Let's head back over here. You're welcome. Great question, Meath. Amazing work. Really great review. Basically understanding all the output. Yeah, exactly. That's what I want right there. Woo! We got 25 minutes. We got to do some data analytics number 5. We'll do a little quick overview of this right here. Not too quick, but we'll do some. Let's check it out. Data analytics number 5 on regression. So if you're wondering, data analytics 5 on regression, we've been doing this. We've been doing tons of regression today. We've been doing regression. So let's check this out over here. Yeah, well, you can resubmit. We'll take a look right here. But good work, Blake. That's an excellent job right there. Let's go do some data analytics regression. Here we go. Regression all day. We just did so if you're wondering, we've already been doing a bunch of regression right here. We're going to download this engagement rings data set. We got 4 conditions. Does anyone know those 4 conditions? What are the 4 conditions for regression? Now, what you want to do is if you're going to name 4 conditions, you probably want to say like my conditions. Everyone's gonna be doing this now. I gotta watch out. I don't want to write too much because we do check for plagiarism, but so I try not to. Little QQ straight enough, no outliers, plot doesn't thicken. So you got some QQ. I'd probably say 2 quantitative variables. Then you probably want to say something like, is it met, not met, met/not met. I'd probably write this out. Met, not met. Hint, you can't make a scatter plot unless it's 2 quantitative variables. Meath knows it too. Nice job. The next thing we would say right here, and then we would explain it. And you probably want to explain it. So met, not met, and then explain. You want to explain it. So we're going to QQ straight enough. QQ means quantitative variables, 2 quantitative. If a greater, probably people might not know QQ. I say QQ, I accept QQ. You might want to say 2 quantitative variables. As long as you explain it in great detail, like tell them what it means. You can call it whatever you want. The right variable condition, you can call it. But you need to have 2 quantitative variables as the first condition. The next condition here is straight enough. Boop. And then we have QQ straight enough, no outliers. Now I like to say plot does not thicken, which is the good way of saying it. Plot does not thicken, which is the good way of saying it. And we got Blake showing some awesome help in the chat for 1,000 points showing how to do it. So those are your conditions, and I'd probably label them pretty clearly and make sure people know if it's met or not met. So I wouldn't leave this way. Do people get what I'm saying? Like, I wouldn't leave it this way. You need to, these are just the conditions. You need to probably clearly say, and I'm making this bold right here so my person can see, I do have 2 quantitative variables. So I would then explain why we have this. Never seen Blake LeBron. So you literally have to have 2 quantitative variables to do regression. You have to have that. Name the 4 conditions for regression analysis and give evidence of whether the regression conditions passes or fails. So you could technically change these from met, not met to pass, fail. We're probably good on most conditions. I haven't looked at this one. I'm not going to look at it, but we're going to do a separate one right here. Okay. So let's talk about these conditions briefly right here. If you have a scatter plot, the only way to get a scatter plot is what? The only way to get a scatter plot is what? And then how would I talk about this condition being met? This is what you're doing. Same sort of stuff, different graphic. How would I talk about QQ being met right here? Like, what would I write as my full sentence? Like, think full sentences. Full sentences. Be verbose. How would you write about the condition being met? This is weight and horsepower. It's a scatter plot too. How would you be very verbose and let people know the quantitative variables condition is met? How would you let people know? How would you let people know? What would you say? And that's good right there. But like, I'd probably say both weight and horsepower are quantitative variables. Thus, I have 2 quantitative variables. I'm just worried everyone's gonna write the exact same thing, and we don't want to have any false positives on cheating. So do not send people your work. So I want people to be very be verbose. So I'm gonna try not to say too much because I don't want any false positives on if I say too much. So with this right here, the next condition is straight enough. Straight enough is talking about the what right here. What do you need to look at to see if this is a straight enough relationship? What do you need to look at? Like, what the whole idea of straight enough is what? We're not going to write it out too much, but you need to be talking about the what for straight enough to say if it's met or not met by looking at this. Exactly. And then go into, so here, wait, Blake, I'm going to remove, just in case, because I feel like that's such a good answer. I'm just going to remove that right there. Yeah, kind of, that's the idea right there, right? I'm so worried that we check these things for plagiarism. I don't want to have any false positives. So make sure you're thinking about your own ideas right here and to talk about it, that this regression line, go be verbose. You just got to talk about that line doing a good job or bad job. And Blake, we're throwing you 5,000 points. Yeah, totally. Oh, I hate it. I spent so much time dealing with it. I hate it. 5,000 points, Blake, right there. Thank you so much, and amazing answers. Since this is more of a written one. Now we might have a little bit of so here, I can explain this one. You can't copy my work now, you're right, because you're not doing this one. I'm a little worried about the plot, or I don't really see outliers. Maybe there's a little bit of an outlier right there. Maybe. You see, maybe. I'm going to say a maybe. I might even put maybe fail. Maybe fail. You see that point right there? I'm saying maybe fail because there's a high point over here. Ooh. But I'm also going to say maybe fail for plot thickening. Because, don't write down these exact words. There might be a small issue with plot thickening on this one because the plot appears to get a little thicker between 3 and 4 weight And notice right here how the plot's getting thicker. It's maybe an issue. So maybe an issue with plot thickening. QQ, good enough. Straight enough, good. QQ passes. Straight enough, yeah. And then no outliers, maybe that's an outlier, so maybe fail. And then plot doesn't thicken, ooh, it's maybe getting thicker in there. Now, what's really cool is we actually have a mathematical way of doing this. You won't do this in 201, but we actually have a mathematical way of checking this regression. And the only one problem is the normality of the residuals, probably due to the outlier over there. And you see it on here on the QQ plot for normality. So that probably is an outlier. Equal spread is fine, but that's 320 right there. So we have advanced ways of looking at it and just finding out like that. So it does look to be more of an outlier issue, not a plot thickening issue. The test returns issues with normality, which would be an extreme value. Technically, won't the data be different for everyone to some degree? Correct. Do take your random sample. Make sure to start, because you are taking a random sample on this one. Take a random sample of 200 plus the last 2 of your TID. Report. So you need to make a regression model right here. So I can show you how to do the regression work. You are going to be predicting and you need to have the title residual plot. Screenshot should include the regression line plus all the regression output and only the first residual plot. Yes, take multiple screenshots. So we want to predict, use caret as the predictor and price as the response. That means price is the response, which is Y, variable of interest. So you want to take a random sample of 200 plus the last 2 of your UTID. So here we go. Table. Subset. Table, subset. Boop. Go down to random sample, 200 plus last 2 of UTID. Put 200. Make sure it's the last 2 of your UTID, like you'd add 11 to it. So it should be 200 something. And then you hit enter, enter. There you go. You know you've done it correctly if you see 200 down here in the bottom left corner. So with this, we have right here caret and price, and they are blue, meaning quantitative. So now we go to analyze fit Y by X. Make sure you're doing it on the one with your 200 plus the last 2 of your UTID. Double check that right now. Analyze fit Y by X. The Y variable is the one we ask, why is this happening? Why do diamonds cost so much? X, well, maybe the caret explains it. So maybe the caret of a diamond explains like how many carats it has, how big that ring is. There's my ring. 0 carat diamond ring right here. So it didn't cost that much. My wife's ring, though, it's got some carats. Got 50 carats. She just so 2 quantitative variables right here does look to be. Now I'm not going to say what issue I see, but I see something. I'm not saying what issue I see. Don't put it in the chat, but I do see an issue with something. A little I see an issue. I see an issue. So let's go ahead and click the red arrow and fit our line. We're going to fit the line to this right here. So with fitting the line, I definitely see an issue. It's at least 1 or 2 issues. And it's probably not this line right here. A hint on that. That line looks to go through the data. That's good. We got an R squared. We got our model. Make sure to take screenshots. What you could do is you could move it. I wonder if I can move it. This is just doing some niceties. You know what? You might be able to get... You can get... Look at this. We moved it. You have to grab the grabber tool right there, and you have to click this and move it. And you might be able to get a pretty nice 1 screenshot on this. It's pretty good right there. It's a good 1 screenshot. There we go. Don't worry how many screenshots you have to take. Just make sure it looks nice. But that was the grabber tool up there, that little grabber tool. If you take multiple screenshots, it's fine. Just be careful on smooshing your screenshots and stuff. You don't want the screenshot to look all weird. You can always crop your screenshot afterwards. Don't get extra portions of your screenshot. Make the screen, how to do 3, that's perfectly fine. Shouts to Blake right there. See that little tiny little blue right there? I say I don't want that blue. You can always crop your screenshots afterwards. Make your pictures look nice. This is part of your grade. You wouldn't get points off for that tiny bit of blue, but the numbers should be readable. Be very careful doing things like this. You don't want to do that. You want to grab on the corners to make it smaller or bigger, and you don't want to grab extra parts of your screen. So you could make it about like that size right there. Send in the screenshot. You're good to go. Screenshots should look nice. Don't worry if you take multiple screenshots. Perfectly fine. I gave all my carrots to my bunnies. I like right there. We're making that a quote. I love anything about our bunnies. So right here, we got that as a quote of the day. So now, quote 322. So now we have the intercept right here. We're just going to write on this output the important values, and we need to grab that residual plot here in a moment. So the intercept is the B0 value right there. That's the intercept and that's the B1. And I'm talking about these values right there, the intercept and the slope respectively, as you can see from the equation of the line, the B0 and the B1 respectively, predicting price. Very important to know, and we've been doing a lot of problems. Check out earlier in this video if you want to see some practice. We've been literally going through labeling multiple equations right here with B0, B1. We were even doing advanced work for 320 or 474, excuse me, where we were going through and doing the same sort of things with the regression equation with the exact same output, B0, B1, R squared. All of that output right here is what you see on what you're analyzing. So we use these ideas in multiple classes, even in 474 with ElasticNet. So all this right here, good to go. Great picture, but we do need one more screenshot. The final screenshot we're going to need right here from the jump output, we have to click under the linear fit. And under the linear fit, we have to click plot residuals. Plot residuals. So we only want the first residual plot, so I'm going to make it look a little pretty. And the residual plot is really telling a problem right here. There is maybe a little bit of an issue there too. Yeah, someone could maybe complain about that. Yeah, they could. Okay. Gotta tell the grader that I do see a secondary issue right here. I see. I gotta show that to Terry and make sure he sees that, and the test does come back saying there's an issue on that. That's where if you look too long at things, you can see too much. But I do see a little bit. My primary concern is the other one, though. I got a primary concern. I do see an issue over here, and my primary concern is this one, though. It's my primary. Does that make sense, Blake? When I'm drawing on this, can you see where I'm saying a little bit of an issue over here? And I'm also seeing a more major concern right here. Like that's more major. The forbidden Wi-Fi bars right there. So we definitely see some issues right here in this residual plot. And a residual plot is a really great way to see if your plot doesn't thicken. Like a residual plot is a really great way to see if the plot doesn't thicken. Yeah, yours might, because yours will be a different random subset. So you might see a little bit different. Do you say to relabel it? I thought I almost said on there, like relabel it. Title residual by predicted plot. Yeah, that's what we got right there. Residual by predicted. Residual by predicted. Yeah, so that's the right one. Cool. Report the value of the y-intercept and its proper interpretation. So the y-intercept interpretation is when x is equal to 0, we expect y to equal b0 on average, with a little on average on there. That is the b0, also known as the intercept. The slope is for each 1 unit increase in x, we expect y to increase by b1 on average. And we should put increase decrease because it depends on if the slope is positive or negative. That is the slope right there, and these values will change depending on what your y and your x are. Make sure to use the y and the x as written in the problem, and 1 unit increase should also be context. I'm going to do some interpretations here in a second on my problem, so you'll be seeing this. So the last but not least, and these are things, Blake, why do you think I'm writing these down for everybody? Why is this so important? Why do you think these right here are so super important? Why do you think we care so much about you knowing this? Why do you think we write these down and we know them and we understand them? Why do you think we know it? Maybe because 12 points on the test? Yeah. Blank percent of the variation in y is explained by the variation in x. There we go right there. And so that's the r squared right here. R squared is blank percent of the variation in y. This is need to be filled out. So I'm going to be interpreting these here in a second for a totally different problem. So stay tuned right here as you hear me interpret these values, write these down, know them, be able to do them, and explain them. I could try that. I never know. Okay, so here we are on a totally different model, and this is not your work, so I like to do different things other than your work, and this is how it would work right here. And let me add one last thing to this. Comment if logical interpretation. There we go. Comment if it's logical. You'll see that in the problem I'm right about to do. Okay. So the intercept right here is negative 1.821, which means a car that weighs 0 is expected to have on average a horsepower of negative 1.821. So that is illogical for two reasons, because cars don't have 0 weight, nor could a car have a predicted horsepower of negative 1.281. The weight right here is going to be for each additional 1 unit increase in weight, which I think is in tons. For each additional 1 unit increase in weight, we expect a car's horsepower to increase by 46.16. Might not be tons. The PLP 50. Nice. It's coming to haunt us. The R squared right here is the percent of variation Y explained by the variation X. So 43.39% of a car's variation in horsepower is explained by its variation in weight. Does that make sense to you, Blake? Do you generally see cars that have higher weight have higher horsepower? Like cars that weigh more generally have more horsepower? Is that what you generally see? There may be some outliers, things far away from the model, but generally speaking, cars with a higher weight generally have more horsepower. And there's other things. There's another 57% of the variation in horsepower that would be explained by other variables. There's things we haven't explained. There's things that are further away, but does weight to some extent explain horsepower? Like heavier cars tend to have more horsepower, like generally speaking. So 43.39% of the car's variation in horsepower is explained by weight, which means there's other things that we haven't accounted for. Like there's other things that explain horsepower of these cars that we don't know. So that's those interpretations right there. Report if it's statistically significant. Define and include the values from the output. So we were just doing this a moment ago. So where in the output do we see if this is statistically significant? Last question. Let me send the announcement to the class, and I need to grab some coffee. Where do we see that this is a statistically significant relationship? We got a lot of output right here, and I'm showing you this output, which looks just like your jump output. Your jump output right here, I'm going to take a screenshot of it. This output, not that one, this output right here, that output right there looks just like that output. So it's the same thing, same exact thing you're seeing as I send the announcement to the class about the class starting in 9 minutes. The significance of the model is found where? The significance of the model is found where? Class in 9 minutes. Class in 9 minutes. Click here. The significance of the model is found where? People probably said it by now. There we go. Save. It is, oh, no one said it. The significance of the model is the significance of the slope. The slope coefficient. Well, I gave that one away. The slope coefficient right there, which you should quote, but make sure also it's not just the p-value, it's the p-value of the slope. The intercept, yeah, make sure to mention also it's the slope. Gary should probably know that. See, this value right here is not the significance of the model. Meath and I were talking about this earlier, where you could also check the ANOVA, which is down there at the bottom also. The significance of the model, which is right here, is the significance of the ANOVA, which is the same thing, which is the significance of the slope. Is that the value of B1 then? Well, the value of B1 is this. That is the estimate of the slope, but the significance of the model is the p-value for the slope, because that's the XY relationship. The intercept, it doesn't matter. The intercept's just an arbitrary point. We don't care if the intercept is significant. It doesn't matter. The significance of the model, which is the p-value down here in the ANOVA, also seen right here. Also, jump gives you that same sort of output. Jump gives you the p-value of the ANOVA right here. You can hover over it. You see that says e to the negative 105. And this one will also say e to the negative 105. Confirming for us, so if you can see right here, if you hover over these and you see that says e to the negative 105, this is the ANOVA we just saw on the other screen, doing the significance of the model. It's the same one, but the intercept is a different p-value. Oh my gosh. Tiny Brian disappeared. Amanda's cracking me up. Well, with that, I need to grab some coffee. We're going to head off here. Great job, everyone. Let me know if you have questions. Make sure to interpret fully, give full sentences, do great screenshots. Let me know if you have questions. Bye for now, everyone. Bye.